If you're going to make an AI explain itself, model-agnostic methods are usually the least annoying place to start. You don't need to crack open the architecture like some over-caffeinated mechanic.
Right. Black box stays black, but you poke it from the outside.
Exactly. Lime is the classic example. You perturb inputs around a single prediction, fit a simple surrogate model locally, and pretend the world is manageable for 5 minutes.
Pretend is doing a lot of work there.
It is. But it's useful when stakeholders want a reason, not a dissertation. SHAP is cleaner in theory, though computationally it can behave like it has a personal grudge against your deadline.
I've seen SHAP plots. Half the meeting turns into people arguing over beeswarm colors.
And yet, they still ask for just one more chart. Permutation importance is another decent option, though it only tells you what matters globally by shuffling features and watching performance fall apart.
Like pulling one brick from a wall and seeing if it's load-bearing.
Precisely. Poor man's forensic science. The annoying part is these methods explain behavior, not truth. That distinction keeps getting ignored by executives with slide decks. Which is why I keep saying the real decision is whether you want an interpretable model design or you want to bolt on post hoc explanations after the fact.
You mean build the explanation into the model instead of decorating it later?
Yes. A sparse linear model, a small decision tree, maybe a GAM if you want a bit more flexibility without losing your sanity. Those are easier to trust because the structure is the explanation.
But they're not always accurate enough.
Exactly. But that's the trade-off everyone hates. A fancy ensemble may perform better, but then you're left explaining it with surrogate methods and hoping the local approximation doesn't lie too badly.
I've had post hoc explanations disagree with each other. That's always fun.
Fun in the same way a leaking roof is fun. If the business impact is high, I'd rather sacrifice some performance for a model people can actually reason about.
Unless the accuracy gap is huge.
Then you need to be honest about the cost. Better a complex model with carefully stated caveats than a simplistic one that gives false confidence. People keep wanting both, like physics has a coupon code.
Fair. But once you're stuck with the complex model, feature importance is usually the first thing people ask for.
Because they want a ranking. Humans love rankings. It makes them feel like they've understood something.
And attribution techniques at least give them a starting point.
They do. Global feature importance can show which variables matter across the dataset, while local attribution tells you why this specific prediction happened. Different questions, same inevitable misuse.
You're thinking permutation importance, SHAP values, integrated gradients, that whole circus.
Yes, though the circus has structure. Permutation importance is straightforward, but can get distorted with correlated features. SHAP gives nicer consistency properties, assuming you enjoy paying for them in compute.
Integrated gradients is more for neural nets, right?
Right. It attributes prediction, changes along a path from a baseline to the input. Very elegant if you like baselines that nobody can agree on.
So the explanation depends on the baseline, the correlation, the method, and the mood of the dataset.
Which is why I trust feature attribution less than people do. It's helpful, but it's not divine revelation. That's exactly why local explanations matter more than the glossy global charts when something goes wrong on a single case.
One prediction, one explanation. Much cleaner.
Cleaner, yes, but still fragile. Local methods try to answer why this customer was denied a loan, or why this scan was flagged, without pretending the whole model behaves the same way everywhere.
So, Lime SHAP, counterfactuals. Basically the why me toolkit.
More or less. A good local explanation should be understandable, relevant, and specific to the instance. If it says a feature mattered but doesn't tell you in what direction, that's not much help.
People always forget direction. They just want a number with confidence and maybe a tiny graph.
Of course they do. Counterfactual explanations are often the most useful. If this value were lower, the outcome would change. That's actionable.
Unless the required change is ridiculous.
Then the model is either brittle, or the domain is. Sometimes both. I once saw a recommendation system explain a refusal by suggesting the user become 6 years younger. Very efficient, deeply unhelpful.
Local explanations are fine, but you still need the bigger picture.
Exactly. Global explanations answer what the model generally relies on, not just why one prediction happened. That's where you see patterns instead of anecdotes.
Like a map instead of a single street.
Yes. Partial dependence plots, feature important summaries, global surrogate models. Those are all trying to describe overall behavior. Useful when you need to detect bias, weird interactions, or a feature the model is leaning on far too hard.
And when it's doing something stupid consistently.
Especially then. If a model keeps treating zip code like a proxy for income or race, a local explanation won't save you. Global analysis is what reveals the habit.
But it can smooth out important edge cases.
Naturally. Global views are averages, and averages can hide disasters. That's why I prefer combining them with samples from individual predictions. You check the forest, then you still inspect the trees that look like they're on fire.
You really do love a dramatic analogy.
Only because the models keep earning them. Deep learning makes all of this more annoying, so visual explanation methods become the default crutch.
Crutch or weapon, depending on who's using it.
Fair. Saliency maps, GradCam, activation maximization, occlusion tests. Those help show which parts of an image or input influence the output. People like them because they're intuitive. A heat map feels decisive, even when it's not.
Heat maps do have a way of making nonsense look scientific.
Exactly. GradCam is decent for convolutional networks because it highlights regions tied to a class score, but it's still approximate. Saliency can be noisy. Occlusion is slower, but at least more direct. Remove a patch, see what breaks.
So basically, poke the model and watch it flinch.
That's one way to put it. The trouble is that visual explanations can be persuasive without being faithful. If the map looks plausible, people stop asking whether it's actually correct.
Which is how bad decisions get a glossy interface.
Precisely. A nice-looking overlay is not proof. It's a lead, not a verdict.